So the first one, what the project is, we wanted to develop a real-time, three-dimensional tracking system using ultrasound positioning. The reason we chose that is because a lot of the principles of ultrasound tracking are very similar to GPS principles. A lot of the signal processing techniques, the basic distance calculations, things like that. So we were working from an established base. However, ultrasound tracking, as opposed to RF, is ultrasound's much more slow. So you can have much lower frequency clock speeds and still get a very accurate signal out of that. If you're trying to read an RF signal and you want to get a millimeter of precision, you need a gigahertz speed clock to do that, just assuming perfect tracking. With ultrasound, because it's so much more slow, you can have a slower clock speed and still gauge a system very accurately. And so that was our main motivation. The basic gist of how our project works is we have essentially an array of transducers, one in each quarter of a cube currently, but it could be any setup ideally. They each pulse towards our receiver circuit, and once we've gotten the full round of pulse, we analyze how many clock cycles essentially passed between the initial pulse and when we received it, spit that all into a bunch of code that does some analysis, does some trig, and get a position out of that. Our initial results are very good. In one dimension, we have a maximum error of about a centimeter. Our average error is a little less than 4 millimeters or so. So very, very accurate for a very low-cost system. In 3 dimensions, the error is obviously slightly higher, but actually there's not really any extra additional error introduced by the code. So it can be modeled essentially as an error cube, and we get about that same amount of error times just root 3. So it's very, very accurate in 3 dimensions. Perceptible to the human eye, but just barely. Looking forward, we'd ideally want to reduce the resonance of the transducer circuit. That was a big problem for us. We didn't have one-to-one signal correlation, so we had to do time division multiplexing instead of any sort of actual signal layering, which severely impacts the update rate, though it's still very fast. We get probably 30 to 40 updates a second or so. We'd like to optimize the device accuracy when moving. That's tied to a higher update rate. So ideally, if we could find some non-resonant transducers, which are produced, they're not really commercially available at the frequencies we would like, we could potentially do that. We want to develop an API for use in the future with this thing, because our main application right now is essentially transporting into a digital environment. We currently have a working app in which we sort of move our receiver circuit around and it displays that movement on screen. So we'd like to use that for potentially CAD modeling or gaming even. Potentially, if we improve the tolerance levels, you could do things like remote surgery with it. The update rate's incredibly quick. But that's obviously far in the future. And we'd like to make the transmitter devices wireless. We're not entirely sure how we sync them, perhaps Bluetooth, perhaps something more low power, but with a fairly clever algorithm, that shouldn't be too hard to do. So, thank you. Any questions?
So what's the primary application for this? Or where would you see this?
So the application we decided to focus in this semester would be essentially CAD modeling. We decided to create instead a basic proof of concept to show that we could output the locational data we were getting on the microcontroller through a USB port, process that, develop a location. So we actually have a working tracking essentially program out. We used OpenGL, just got a sort of basic model up, and as you move the receiver around, the ball tracks inside the essentially little window we have. It's pretty basic right now, but that would ideally be the eventual application. We want to sort of develop an API for that first before taking commercial.
Who's your fourth member?
Our fourth member, Matthew Rennick, he's actually a sophomore, so he's not in this senior design class, but he's currently taking a final, I believe. So.
But the team was set up in such a way, they had extra help, and Matthew would probably continue with this project when his time comes for the design.
What was your biggest pain now?
Chris can speak to that.
Yeah, I think
Interesting.
one of our, so after senior design 1, we actually had a working, just one-dimensional system that worked really well. Like Ben said, we had our maximum error was about a centimeter. So the biggest problem with this was trying to move that into a three-dimensional system. And what we thought about doing, initially we thought, if we stick a transmitter in each corner of a cube, we can, you'll be able to see enough that you'll be able to find reasonably be able to find a position out of it. And it turned out that one of the biggest problems was, one, getting the receiver in the middle to see enough transmitters to, I didn't think that would be a huge problem, but it ended up being quite a challenge, getting to see enough signals to register something, and then actually taking that and figuring out where, you know, X, Y, and Z, where that was in the cube. That, and it turned into quite a few nights of me scribbling the rig and trying to remember how to.
I believe my favorite error though was actually, we had some wire crosstalk that allowed our system to still work for a little while, but with a much, much weaker signal. So it was working, so we couldn't quite figure out what was wrong, but it was incredibly weak and just like jittery. It was interesting. It's actually just
Like, not learning about how.
interesting soldering problems. Yeah.
So what kind of accuracy did you get in the, you said improved precise accuracy when moving, so you're able to move it around
Yeah, it
during 3D?
pretty quickly. There's a tiny bit of jitter right now.
There is a tiny bit of jitter in order to, what we were doing originally in Senior Design 1 is we had just that one-dimensional system. So we had actually a ring buffer of it would just send a measurement, calculate it, figure out about how far that was. And if you did that enough, it would move a little bit, but if you took an average of, say, 10 samples, you get actually a pretty accurate measurement. With this, with doing so many, it ended up killing our update rate trying to do that. Because what would end up happening is you could only see maybe half the transmitters, depending on which way the receiver is oriented. So the rest would sit in timeout. So if I kept that ring buffer in, the update rate